cardiovascular system by addressing what's going on with the blood. Remember, blood's main roles are going to be transport, and then because of what it transports, it's going to be involved in regulating pH and temperature and monitoring what's going on in the bloodstream in terms of microbes and like that. Um, Now, what's dissolved in blood is a really big deal. And so that liquid part of blood, the plasma, is very, very significant. Keep in mind that blood is a connective tissue, so we refer to this plasma sometimes as being the matrix of this tissue. And that matrix is unlike the matrix of other connective tissues and most other tissues in our body in general, because it's about 90% water. Obviously, that water is necessary in order to dilute and transport all of these substances, but it does create some issues in that that means that the water, being kind of more concentrated in the bloodstream than it is in other places, is always going to be kind of wanting to exit the bloodstream. In addition to the water, there are also proteins in the bloodstream, and those two components together make about 98% of blood. And then there's the 2%. You might go, well, what's in this 2%? Well, we refer to this as solutes, and the solutes are all the nutrients, all the gases, all the wastes, all the molecules that are being transported from point A to point B, all of the other components. And really, that 2% is what really makes blood blood at the end of the day. The water's there and it's important, and the proteins are there and they're important, but the solutes are the reason for blood. So the plasma has its components, and then the formed elements, all the cells and cell fragments, each have their own specific roles to play as well. The proteins that are suspended in the plasma come in three forms. There's albumins that contribute to what we call osmotic pressure. This is what holds water in the bloodstream. This is why blood can be so water rich, is because albumins draw water towards them like little sponges. They also can grab onto and transport certain molecules, some of which can't move well through an environment that is so wet. And so they're really critical in making sure things can move through the system. Globulins we know a little bit better, mostly as antibodies, immunoglobulins. They also act as transporters, especially for fatty substances like cholesterol, which again, you might imagine, would have difficulty moving through such a wet environment. And lastly, we have fibrinogens. They are actually in a liquid when they are in their natural state, and they get activated by something called thrombin to become fibrin. And fibrin is the solid mesh-like net form of this protein. So fibrinogens are liquid, and fibrin is the fibers, the net that can form a clot. And that net is really important. It'll trap platelets, it'll trap red blood cells, and start the process of repairing the damage that is there. The fibrin doesn't actually do any of the repair, but it makes it possible. It provides a framework where that repair can take place. The cellular components are called the formed elements, or the cellular elements. First one is the erythrocytes, or you probably know them better as red blood cells. And this is a really nice example one here. Notice that it's concave. I think of them like jelly donuts that aren't full anymore. I got all the jelly out already. This image actually also has a really nice job of showing some different white blood cells. This orange one is a white blood cell. The green one is a white blood cell. And these little purple blobs are platelets. Just a reminder, no, they are not actually orange, green, and purple in real life. Those are colorized to help us distinguish between them better. And you might be going, well, of course they are, Mary, but I do have people ask every once in a while. So what makes red blood cells kind of unique is that they are flattened like that because they have no nucleus. That's really interesting because that means they can't repair, and it also means that they can't reproduce. So red blood cells do not make more red blood cells. Okay? They're going to live about 120 days and for the most part be trapped in the blood vessels at all times. There are only a few places in the body where red blood cells are allowed to kind of go freely into a tissue. For the most part, they are contained always. They contain a protein called hemoglobin that's really the big oxygen and CO2 carrier for us. And since they can't repair and reproduce, they are constantly dying off as they do their job until they get banged up and beat up enough that they can't do it anymore. And our spleen and liver are going to help filter those out and recycle all of the things in them. Because some of the things in there, the hemoglobin, but in particularly the iron that is in them, is a valuable resource to our bodies. And we want to recycle that, not just let it be removed from the body as a waste component. Hemoglobin is our oxygen transporting protein. You have to have iron to be able to make it, but there are also other critical components like folic acid and B12. So it's not just iron, although that's the one that gets the most notice. And when it's carrying oxygen, they often refer to that term oxyhemoglobin, and when it's not, deoxyhemoglobin. And there are millions and millions of hemoglobins in a single red blood cell. Now, I'll be honest, when I was in college, I looked at this and I went, oh, well, let's see, there's a hole in the middle, so that's the hollow spot in my cell, and this is the outside of my cell, and there's one big red hemoglobin in every red blood cell. I was totally wrong. There are millions of hemoglobins in every red blood cell, and each one has 4 of these heme groups with an iron in it, and each one is able to carry 4 oxygen molecules. So 4 times millions of oxygen molecules on every single red blood cell. As these are dying off, we need to then, of course, replace them, or we won't have enough supply to transport our oxygen. And so there's a hormone that comes from the kidneys called erythropoietin that is going to be produced when we're low in oxygen in our bloodstream, and also when there's low blood pressure, which you might think is kind of odd. But when our blood pressure is low, one way to bring it back up is to put more cells in the bloodstream, and they'll kind of pull water towards them to keep flow going. So red blood cells are useful in bringing up blood pressure because they attract water. Obviously, also, if we had blood loss, that would be a time to make more red blood cells. If we go to an area where oxygen is not high in availability, like if you go up into the mountains, your body will naturally produce more red blood cells in response to the depleted oxygen levels in the air. That way you have more to gather, more cells to gather that oxygen. And that erythropoietin is going to go to stem cells in our bone marrow called hemocytoblasts, blood cell builders, right? Remember that from back in the tissues lecture? And those hemocytoblasts are really where we get everything in. So this just kind of shows that cycle. Hypoxia, that's low oxygen. Erythropoietin gets released, goes to the bone marrow, tells our bodies to make more red blood cells, and then they can carry more oxygen, which should improve our situation. When these start to die out, because keep in mind that, these red blood cells have to squeeze through our capillaries, and our capillaries are only about 1 cell thick. In fact, they're a little narrower than 1 cell thick. So, if this is my capillary, the size of the red blood cell that has to fit through it is about like this, which means that to fit through there, a red blood cell has to bend itself just a little bit. And that's why they're hollow. That's why they have no nucleus, because it gives them more flexibility to squeeze through. But because they're being bent and manipulated all the time, they get beat up and banged up over time and have no way to repair because they have no nucleus. So they die off fairly quickly after only about 3 to 4 months. As they die off, your body is going to process them through the spleen and liver. The iron gets held by the spleen. And so in some cultures, the spleen is considered kind of a culinary delicacy. And it's generally reserved for like young men and pregnant women. The young men, for example, of like hunter-gatherer tribes would eat the spleen of an animal because it would make them strong and give them lots of iron. And pregnant women are often encouraged to eat meats like that because, again, it has lots of good nutrition for the growing baby and the mom to help keep them healthy. The protein component, the rest of it, is going to go to the liver and get broken down through a series of steps into bilirubin. And the bilirubin actually goes into our digestive system to be bile salts, so part of our digestive juices. If the body is not able to do that, break things down like it's supposed to, if the liver can't do it, I should say, the rest of the body can actually take over the job. All of your cells can do this, but it's not great for them because bilirubin needs to kind of be contained in specific locations, or it can start to cause malfunctions in cells. It's a toxin. So if that starts happening in the cells of your body instead of in your liver, you'll get jaundice, just a buildup of bilirubin. We sometimes see that in premature infants because their livers just aren't quite ready to start processing those red blood cells that are dying off in their bodies. We see it in people with like hepatitis, for example, because their liver isn't functioning properly anymore. And if we think about it, that would be large scale bilirubin processing. But on a small scale, anytime you get a bruise, we see the same thing happen. Because when you bruise, of course, you damage the blood vessels under the surface of the skin. The blood leaks out there. Well, it can't get back to your liver to be broken down. So first it turns black and blue because the oxygen has leaked out of those cells. And then it starts to turn yellow and green. And bilirubin and one of the other products of the breakdown called biliverdin are yellow and green. And if you've ever dealt with someone who has jaundice, you might know that they encourage us to put them under sunlight because radiation will help break down that bilirubin more rapidly. So there's always the kind of the old wives' tale of you should put your preemie jaundiced baby by the window a lot, right? So that they could get the sunlight. And in fact, what they do in the hospitals is basically that, is they put them under high intensity lights to help their bodies process through that bilirubin more quickly into less toxic compounds. This is actually my oldest son. He's almost a teenager now, but he was born 11 weeks premature, and he had to spend a couple days under the sun lamps, I always call them, to help get his bilirubin levels processed down. And a lot of times we don't talk about what happens if your body can't process through those toxins fast enough. It actually goes up to the brain and starts to cause malfunctions in the nervous system. So this is important that we get that under control and manage that, not just let it go. The other condition that we sometimes hear quite a bit about is anemia. And I mentioned that iron, folic acid, and B12 were all important in making red blood cells. And so, it's certainly true that a fair number of people are iron deficient, and that is why they might have anemia. There can also be other nutritional deficiencies that lead to low red blood cell counts. Hemorrhagic anemia would be caused by blood loss. I remember an instance of a friend who mom was anemic, and the doctor was prescribing lots and lots of iron, and numbers weren't going up like we expected them to. And she goes back in the doctor's office, and he does an exam and goes, "What's this big bruise on your side?" And she goes, "Oh, yeah, I fell about 3 months ago, and this bruise has been there ever since." Well, it turns out she had some very mild internal bleeding going on. And so her low blood count levels were because the blood was leaking out into her body cavity rather than flowing through her vessels like it should have been. So always important, if things aren't progressing like expected, that we be a little more thorough and in-depth and not just, continue with our assumptions, I guess would maybe be a good statement. Last kind I want to talk about is sickle cell anemia, which is a hereditary form of anemia, where the protein hemoglobin is formed incorrectly, and therefore the cells are formed incorrectly. And look at those spiky, sharp cells. Can you imagine as those try to go through that single width of a capillary, how much damage it would do? And so people with sickle cell anemia often have extensive bruising on their bodies and often don't live a very long lifespan because their bodies just can't repair the damage that is done quickly enough. Next type of cells that we find in the bloodstream are the leukocytes, or white blood cells. They are all of the cells involved in the immune response. Lots of good stuff about them in the lymphatic system, lectures. One thing that is kind of unique about them is their ability to not just stay within the vessels, but also to exit the bloodstream and go out into our tissues. There are at least 5 different kinds of white blood cells that we commonly talk about, and we can distinguish them by the presence of proteins. So you see how these ones have more purplish out in their cytoplasm, and then by the shape of these nuclei. And look at some of these funny shaped nuclei. One is tri-lobed, has 3 distinctive parts. Some are horseshoe shaped. And each is designed to respond to slightly different ranges of microbes and events in the body. And so they're specialized, and that means that if we count how many of each type we have, we can actually make some pretty decent predictions about what might be infecting your body or what kind of problems might be going on in your body. The first one is the most common one. It makes up about 60% of your white blood cells, and these are neutrophils. They're our first responders to infection, and they're really good against bacteria for 2 reasons. One, they can engulf or phagocytize those microbes. Secondly, they secrete something called lysozyme, which is a natural antibacterial. And so that combination means they're really good against bacteria. It makes sense then that they would be the most plentiful because bacteria are all around us. And so this is the most common thing the body thinks it needs to protect itself against is bacteria. So lots of responders because there's lots of exposure. Love this picture. It's obviously an artist's rendering, but of a white blood cell emerging from between the cells of the capillary and then coming out and grabbing these bacteria and pulling them in to recycle all of their components. Then we have eosinophils and basophils. These are both present in much smaller numbers in the bloodstream. I believe it's the eosinophils are about 5% and basophils are about 2%, so very small quantities. Eosinophils tend to be involved in allergic reaction because they're supposed to be secreting suppressor molecules. They're supposed to tell the body when enough is enough and that we are done responding to whatever foreign matter has entered our system. If they don't do that, then the response can get out of control and you'll get itchy and sneezy and all that stuff. They also are able to secrete some specific chemicals when there are parasitic worms, like the heartworm that your dog gets would be a parasitic worm, and that kind of thing. I would point out ringworm, which is a skin rash, is not actually caused by a worm, it's caused by a fungus. Bad name. So worms in humans are much rarer, but this is why, like Grandma always said, you had to cook your pork to within an inch of its death, is because of the risk for parasitic worms that might be growing in the pork. These days, we have a very safe meat supply by comparison, and so that risk is very low. We don't have to cook things quite so thoroughly as maybe Grandma did. But they're designed to respond to that type of thing. Basophils, some of them actually flow through the bloodstream and some of them actually sit in particular tissues. They release histamine, and so they also can be involved in allergic reactions. And histamine is designed to bring blood to an area So it dilates the blood vessels, and in particular, it also tends to constrict airways so that um, if the thing that is infecting us is coming through our respiratory system, it's blocked from being able to do that. Now, in a severe allergic reaction, that means that you tend to get a rash, or your blood pressure can get low, and that you have shortness of breath and difficulty breathing. But under normal circumstances, those reactions should actually be good things. Next is the monocytes. They make up about 10% of our cell population. And they're kind of cool because they transform from their monocyte form into what we call macrophages when they're mature. So when they come in contact with foreign matter, they transform from just these kind of survey cells into these microbe engulfing, destroying cells. And they do two things. They stimulate other cells. They're what we call antigen presenting cells, APCs. Go down here, antigen presenting cells. And what that means is that when they come in contact with something foreign, they don't just engulf it and recycle it and make it disappear. They actually take little bits and pieces of the debris and the things that they have recycled and stick it on their cell surface. And that way, when they come in contact with other cells that are better at identifying what is getting you sick, they can show it to those cells and go, hey, I found this over in aisle 7. Do you know what this is, and do you know how we should get rid of it? And so this is a really important role. Have you ever heard of the idea that you can learn a lot about somebody by looking through their garbage? Well, I think of macrophages as garbage trucks. And not just garbage trucks that come and collect everything, because that's kind of what they do. They pick up all the debris and crud from an area where there's an infection. But they actually stick the interesting bits from where they've been on the outside of the truck. So you can kind of see what kind of things people throw away in that area. And that's going to help your body better respond. Last group is the lymphocytes. They make up about 25% of our white blood cell populations. They come in 3 types: B lymphocytes that mature in the bone marrow, T lymphocytes that mature in the thymus, and then what we call natural killer cells. Now, the B and T lymphocytes are part of our super targeted version of our immune response. They actually can identify specific kinds of bacteria and viruses and launch an attack that's tailored to just target the microbes that are causing the problem. Natural killer cells are not nearly so good. The B and T cells are snipers of the immune response. Natural killer cells are more like the infantry or the bomb brigade, because what they do is they go in and secrete a substance called perforin. And that perforin doesn't just target the infectious cells, it targets the whole area of infection. And that name perforin, I hope, makes you think of perforate, to poke holes in. So it puts holes in the cell membranes of any cell in the area where the infection is. Well, your cells have cell membranes, and if you poke holes in them, they will burst. So there's a lot of collateral damage when natural killer cells go into an area. But it's a common strategy to go in, kind of blast the area where the problem is, and hope that more of the good cells survive than the bad cells. Yeah, and in the short term, this might be a good method of controlling an infection. In the long term, again, lots of collateral damage, lots of side effect for the body as a whole. But one of many strategies our bodies use, and more about that in the lymphatic system lectures. Last but not least, we have the platelets. These are fragments of cells that help our vessels and blood to clot when there's damage. There's actually kind of a small scale clotting process and a large scale clotting process. So the small scale version is just called platelet plug formation. And if you have a very small bit of damage to a vessel, then your body will just do this, where there's a little bit of damage, okay, no terribly big deal. The platelets stick to exposed bits of collagen and they plug up the hole. If it's a small hole, that's not a big deal, no problem. If it's a larger hole, we actually talk about the coagulation or clotting process. In that process, it's a bigger amount of damage, so much damage that chemicals are actually released from the surrounding tissue. And those clotting factors come in somewhere between 60 to 100 different forms. And they have what we call a cascade effect, where clotting factor A triggers clotting factor B, triggers C, maybe triggers D and F, and so on and so forth, and these complex pathways. But at the end of all those pathways, we see fairly consistently a protein called prothrombin get converted into thrombin, and the thrombin converts fibrinogen into fibrin. And that's what makes these nice meshy nets. And this is a really nice picture of them with all the color enhancements there. And those are going to collect platelets and red blood cells and form a nice chunky clot. Now, if that clot stays there for a long time, that could limit blood flow. If it detaches and wanders off somewhere, that could limit blood flow. So as well as having these clotting processes, we also have anticoagulation or declotting processes in place to make sure that they're only there while we need them during the repair process, and then that they get dissolved away and don't cause problems in other parts of the body. There are a couple of disorders related to the clotting process. Particularly, we hear about hemophilia. Hemophilia actually comes in a lot of different forms. We most commonly think of it as a failure of the blood to clot, which means somewhere along that domino effect of chemical reactions, something's not triggering the fibrinogen to turn into fibrin and make that meshy net. Hemophilias can also be the opposite way, where there are excessive quantities of clotting, which can be equally bad. So, not clotting is not good. Clotting too much is also not so great. All right, that is the end of our little overview of blood, and that should wrap up our cardiovascular discussion.